to build up to the idea of how to change basis, we're going to introduce something new. Now, if you notice, there was no pre-quiz associated with these exercises. The reason being, I'm working under the assumption that I think, and I polled you, that one of you maybe or two of you have seen tensors at any level before. Most of you have not. And one thing about this particular course is there's two things that we do. One is we review ideas you've seen before, and those are ones I expect you to have mastered by the end of the quarter for the exams. Then I introduce new ideas. These are ones I expect you to be confused by and hopefully understand the next time you see them. So the point of introducing it in this class is so that when you next see it in the next 2 years, it's that much more familiar to you. If you happen to be lucky enough to have seen it already, then hopefully this will help you master it. And for some of you, if you're naturally gifted at tensors, you might get this right away. But be aware that this falls into very much the category. A lot of physics I describe as incredibly hard until you understand it. Then it's trivial. And you won't really remember how it could have been hard before you understood it. So there's really, with tensors, there's no sort of partially understanding them. You either really understand them or you're really confused by them. That's my experience. Now, you might break that mold and be partially confused, but trust me, it's unlikely. The reason we talk about tensors is ultimately we're thinking about physical vectors, and those are things with direction and magnitude. Now, what we're going to see next week is that, strictly speaking, the mathematical definition of vectors and vector spaces does not involve direction and magnitude. Those don't exist for vector spaces. There's something you impose upon a vector space when you get the idea of a dot product or a scalar product. So it comes later. But geometrically and physically, we have a good intuition for direction and magnitude. And we also realize that lots of objects have more than one direction. And that's why we build up this machinery of tensors. And it's all centered around how components transform under rotation. So the focus is on rotations as a linear transformation on basis or components. And this is where we're going to have to realize we're going to write second-rank tensors as matrices. But tensors, all matrices are not tensors. All second-rank tensors can be written as a matrix just because of the way their components are. So that's something you're going to want to keep in mind as we go forward. Now, the starting point, as I said, is how things transfer under rotation. So in 2 dimensions, we already wrote down the simple rotation by an angle theta of the basis. So notice the minus sign is here because I'm rotating the basis, not the vector. This is all about changing how the components change when you're under a rotation of the basis. Sorry, I should have put that there. Now, this is for a 2D case, but more generally, for a 3D vector, one way we can define it then is 3 numbers that transform according to, and I'm going to use the notation from the book. For some reason, they use A instead of R. A So the basic idea is I have 3 numbers, Vx, Vy, Vz. And if under an orthogonal transformation A, they transform by this rule, this is a vector, or a rank 1 tensor. So at this point, you just want to take this as a definition. And with that definition, I can now define tensors of all sorts of ranks. So a 0 rank tensor is a scalar, and it's just a single number that stays itself under any rotation. So 0 ranks means you use no matrices to transform it. It's just that number. It has no indices, no direction, just magnitude. The rank 1 or 1 rank tensor is what we normally think of as a vector, and it has a single index, which we'll see is what we use to keep track of how it's transforming under the matrix. And then the final one we use a lot is the second rank tensor, which when we're being lazy we just call a tensor. And you have to realize that that's lazy language. You just call that a tensor because you have a rank 3 tensor, you have a rank 4 tensor. It keeps going. And this effectively has 2 directions or 2 indices. And we're going to see that that means it uses 2 matrices to transform itself. Now, physically, I'd asked this question before, but can you think of physical situations where you'll have an object that is used to describe 2 directions?
Rotations around multiple axes.
Yeah, okay, yes, but what is the, when you're dealing with rotations, what's the main physical thing you need to worry about? If you're going to try and rotate an object, moment of inertia. Why does your moment of inertia involve multiple directions? What does it connect? What is your moment of inertia? What 2 physical quantities does your moment of inertia connect?
Mass and length.
No, that's how you find it. What equation has moment of inertia in it?
Rotation, torque.
Okay, torque equals what?
I alpha.
Torque equals I alpha. What else has moment of inertia in it? Not its definition. What does the angular momentum equal?
I omega.
I omega. I hate to say it, you need to remember your freshman physics. just a hint. Now, notice, when you did these as freshmen, you treated these numbers as scalars. And scalars are one way you can get from a vector to a vector, right? If I multiply a vector by a scalar, I get a vector. But in fact, these are tensors. They involve 2 directions. They connect the direction of omega with a particular direction of angular momentum, or the direction of alpha with a particular direction of torque. And so what we're going to see, if we write these as indices, we will have to write things like the ith component of the torque is related to a particular number from the moment of inertia tensor times the j component of alpha. So it's this type of notation that we're going to want to understand. And this is going to be a sum because it's a repeated index. But the important point right now is to notice this object is not a scalar. It's actually a tensor, and it's a tensor because it involves connecting objects who can both have their own direction, and you've got to be able to connect all components. This happens with stress and strain. Stress is forces acting on an area. Yes?
Our second rank tensor is multiplied using like cross product.
You'll see it's the equivalent of a dot product when I have 2 indices like this. Yeah. It's basically matrix multiplication. You multiply the row times the vector. So stress connects forces on an area. We've already said area is a vector with a direction. Forces have a direction. We're connecting 2 things with directions. So you need to know all the directions the force might have and all the directions your area, your surface might have. Dielectric constants. Those connect electric fields and currents. And again, the electric field has a direction. The current has a direction. So you have to connect all directions of these. Now, there's lots of ways of looking at this. I do want to kind of highlight the notation from Boas because you're going to have to read it. And the basic idea of how you get this is really from a projection. So let's go back to our I hat, j hat, k hat notation. We can write the vector r in either basis. So this is in the two bases, I hat and then all the primes, and the components unprimed and primed. Now, if you wanted to know the component of R in the I hat prime direction, what mathematical operation do you do? Don't tell me just read off the x prime. Pretend it was more complicated than this. What mathematical operation do you do to get the component of one vector in the direction of another vector? You dot it. Scalar products or dot products is how we project. So I'm going to do I prime dotted into R. And using that basis, that'll get me x prime. Now, I can use the other basis. So that'll get me I prime dot I times x plus I prime dot j times y plus I prime dot k times z. And these numbers here are just cosines of angles, right? Because these are unit vectors. And what's the dot product in terms of magnitude and cosine? It's AB cosine theta, where theta is the angle between them. And if A and B both have magnitude 1, these are just cosines. So we call these the direction cosines. You can write them in more complicated ways, but basically that's what they are. They're the cosine of the angle between them. Now, we can write these just to give you the notation of the book. They like to use a little table. And they give them letters, L1 through L3, M1 through M3, and N1 through N3. And if you look at it, for instance, L1 turns out to just be I dot I prime. M1 is J dot I prime, I believe, yeah. And you just work through the matrices. So that's just to give you some notation. So the book will call these the direction cosines, and that's where they come from. That's less critical than understanding the following situation. I'll leave that there for you to write. The main point is we can now write R prime as some matrix times R. And this matrix is orthogonal. So that means, how do I write R in terms of R prime? What do I multiply R prime by to get R?
Transpose?
Well, yeah, the transpose. And why do we use the transpose? Because this was orthogonal. This is why that's why we spent last week doing orthogonal matrices. So this tells me A inverse equals A transpose. So life is a little bit easier. We can use the transpose there. And now, what I call the useful but confusing thing that's going to take a while to get adjusted to. If we want to write this out in components, we will write VI prime equals the sum. Now this is in 3 dimensions. One thing to keep track of, dimension and rank are unrelated. I can have an 8-dimensional rank 1 tensor or an 8-dimensional vector. That'll have 8, instead of 1 to 3 here, I would do 1 to 8. I could have a 16-dimensional rank 2 tensor. That would have 2 indices, each going from 1 to 16. So the dimension tells you what the index goes over. This is the dimension. The rank is how many indices you have. So my vector Vj is rank 1 because it has 1 index. But it's dimension 3 because that index takes 3 values. And then Aij is my transformation matrix, which I am now going to switch to summation notation again. So the j is summed over. So now you see why this is kind of like a dot product, because I'm summing over the index. And this is exactly matrix multiplication. If you go back and look at how we define matrix multiplication, that's how it should work. So a vector transforms this way. If we want to go the other way, we're told VI equals AIJ transpose VJ prime. So this is A transpose the ith j component, which, of course, is just AJI VJ prime. Because by definition, the ith j component of A transpose equals the JI component of A. Transposing is switching the indices. So notice this no longer looks like matrix multiplication in the normal sense. If I was to turn this around, this is V prime J on the left, AJI, to get the sum, but I'm still summing over J. So it's a little bit different. So you got to watch in your index notation where you're summing. And now, the big final piece that we get to do. You all ready? You excited? The tension's mounting. How the heck do we take a general rank 2 tensor, right? So now I have two indices, and define and/or write it? Well, we use two transformation matrices. One for each index. And this is basically, not basically, this is your definition of a rank 2 tensor. So in 3 dimensions, how many numbers make up Tij? 3 dimensions, how many numbers in Tij? 9. Why 9? It's 3 by 3 basically. So there's 9 numbers. So if I give you 9 numbers, and I tell you if I change my basis using the matrix A, the orthogonal transformation A, that those 9 numbers become these 9 numbers according to this rule, I have defined a tensor. I know it's a weird way to define an object, but it's defined by the fact that it behaves nicely under this change of coordinates. Now let me ask you this. Is this, as written here, matrix multiplication? Think about that. Talk to the person next to you. I'm going to rewrite it here. Is this expression standard matrix multiplication? Who thinks this is standard matrix multiplication? Who thinks it's not? Who's still unsure? That'll always be the third option, so if you don't want to commit to yes or no, I will give you unsure as an option. What is standard matrix multiplication? Well, first of all, here's the really cool thing if you've mastered component notation, right? This index and this index are what? They're the same, so what do we do to them?
You add
We sum over them. Repeated index, we sum. What about these two? They're repeated, we sum. Now, what about each of these individual numbers now? Are they a vector? Are they a scalar? Are they a tensor? Nah, they're each. This is the trick question. When I write it this way, I'm writing the whats of the tensor and the matrices. Components. And components are always scalars. These are scalars. And what's true about scalars? When you multiply them, they do what? They commute. See, you have to remember everything you learned in kindergarten. You learned about commuting, right, in kindergarten where multiplication commutes. Isn't that where they teach that? So, you know, you, you have the commutation and multiplication. So I can write this as AKI Tij Alj. Right? I can switch this T and A. Nothing wrong with that. Now, does anything in here look like matrix multiplication to you? Because what's the key about matrix multiplication? How do I multiply two matrices? I take the rows times the columns and do what? And sum those elements. Do I see any row times a column summed here?
T and the AKI.
These have a row and a column summed. So this is matrix. What about here? Is this matrix multiplication? No, because that's a column and that's a column. I mean, that's a row and that's a row. Sorry. No, I said it right the first time. Column and a column. Yeah. So that's bad. But what can I do to this? How would I make this times this matrix multiplication? I would do the transpose. So I can write AKI Tij A transpose. Just to be clear, I'll put parentheses. JL. And now what do I have? Matrix multiplication, matrix multiplication. So now I can switch from component notation to matrix notation. So this is what we'll call index notation. And notice the power of it was I was able to manipulate it very easily because everything's a scalar. So I can switch things back and forth. And what I end up with in matrix or vector notation is T prime equals AT A transpose. And this is how we change the basis for what we'll see later, a linear operator. And so notice it's not just as was asked earlier, it's not just A times T. That's how we get a vector. To change the basis of a matrix or a rank 2 tensor, we use this. Now,
does that only work for orthogonal matrices?
Well, we're going to do it in general. For if this was not orthogonal, what would we had to have used? A inverse somewhere. And we'd have to derive it slightly differently. Because notice we derived this because we were able, this is just based on, this is true for all tensors under orthogonal transformations, and we use orthogonal transformations to define tensors.
Oh, okay.
So it's very specific. Now, here's an important thing. So in Boaz, all of this stuff is done on page 499 in the chapter on tensors. We're going to skip back to page 151 when we do vectors. And so this is a key notational thing that you need to deal with in your life. We define this in terms of an A that did that. That was orthogonal. So A transpose did that. And then we got that. Later on, we're going to define a transformation C that does that. It may or may not be orthogonal, but its inverse certainly does that. And now the new matrix M prime will be C inverse MC. Notice if C is orthogonal, then C inverse will equal C transpose, which, if I compare the two, happens to equal A. And these two things are the same. I'm just putting the notations in different places. So you will see both this formula and this formula throughout your life. And notice what it depends on is, are you defining the change of basis that takes R to R prime, or the change of basis that takes R prime to R as your initial matrix? And that determines what your inverse is. That determines whether it's C inverse MC or whether it's AT A transpose. And it has to be orthogonal for the inverse to become a transpose.